Hi everyone, welcome back to my channel. I'm Abhishek Podil. Today I'm gonna do a derivation from fluid kinematics, and this is the derivation of continuity equation in cylindrical polar coordinate system. For this I have taken a three-dimensional system, and I'm just drawing a small parallelepiped in this space. Okay, to draw the parallelepiped I have drawn some dotted line here which are parallel to each other. So let's make a small parallelepiped in this space. Okay, so this is how I'm gonna do. I'm gonna draw a small parallelepiped here. Okay, you can see here this is a theta, and this is theta. Here I have just marked 4 points here. 4 points here, and let's draw a vertical line up to this point and vertical line up to this point, and the vertical line up to this point and vertical line up to this point. Okay, so I've got a small parallelepiped here like this. And this is also d theta, and this is also theta, right? And I've constructed a small parallelepiped, and I'm gonna name these 8 points here. That is P, Q, R, S, T, U, V, W, right? P, Q, R, S, T, U, B, and W. Okay. For the analysis, it's better to name a parallelepiped. Okay. So I've constructed a small parallelepiped and named it also. So let's mark this point P. Let P be a point which has coordinate r, theta, and z. All right. So this one is a r, and this one is a theta, and you to mark a z, you have to understand, like you have to draw this at this point also. So let's draw a parallelepiped in this plane. Here also this is d theta, and this is r, and you can just join this one. And this one is a z. Okay, this P point is at a distance z from the plane. So P is a point where it has a coordinate r, theta, and z. To express this in terms of just like a Cartesian coordinate system, you can express the point by locating it from this z at a distance r, and the angle theta, and from this bottom plane z. Okay, so P is located at r, theta, z. Okay, so now this let V velocity components B, VR, B theta, and Vz in this this polar coordinate system, polar coordinate system. Okay, so VR, V theta, and Vz are the velocity component in polar coordinate system. And rho is a density. Rho is density at point P. So rho is a density at point P. Rho might vary. If rho varies, then that is called a compressible flow. If rho does not vary, that is called incompressible flow. Okay. So for the better understanding, so we have drawn a parallelepiped here, which is at a distance r, and let's mark the P point at a distance r at an angle theta and a vertical height z. Okay, so let's go to the analysis. So let's find out, let's understand what is the mass flow rate first, okay? So mass flow rate means mass by time, and mass means volume into density by time, and volume by time is discharge and density into discharge Q, and finally rho into area into velocity. The expression, okay, I have done this in my previous video also. So rho into area into velocity is the expression for mass flow rate, okay? So we have to find out the mass flow rate entering and leaving this parallelepiped. All right? So let's find out. So let's find out the mass flow rate entering the parallelepiped from the different phases, okay? So now let's go to find out the mass flow rate entering and leaving from this parallelepiped. All right? So I'm going to find the mass flow rate entering the phase, mass flow rate entering PQRS, rate entering PQRS, okay? So from this point, let's look at my tip of the marker. In this point, the mass entering from this point and leaving from this phase, entering from this PQRS and leaving from the TUVW. All right? So write the formula here. Density into velocity into area is the expression for mass flow rate. And how much is the velocity? Velocity in this direction. Velocity in this direction is how much? Vz, all right? Vz, because this is a z direction. So the velocity must be Vz. And area is, listen here, the area is, this one is dr, all right? This one is dr because this is r and dr, this is an element. So if this is r, and this must be dr, okay? This must be dr. So if this is r and d theta, this must be r d theta, okay? This must be r d theta. For a small angle, you can write this as r d theta. So you can write this as r d theta, this is r d theta, okay? So, and this is dr. So in this direction, r and dr, the elementary distance dr, and this is r d theta. You have to understand, if this is r, and this must be r d theta. So what is the area of this PQRS? You can easily see the area of PQRS is dr into r d theta. dr into r d theta is the area of this phase PQRS. All right. So now this is the mass flow rate entering the PQRS. So we also have to find out the mass flow rate leaving UTWB, okay? So let's find out the mass flow rate leaving TUVW, okay? Mass flow rate leaving TUVW, that is rho Bz dr into r d theta plus del rho Bz into dr into r d theta divided by which direction? This one is z direction, all right? So that's how you have to do del z into dz, okay? This is the mass flow rate leaving the point, TUVW is the mass flow rate leaving the point TUVW, okay? So now let's find out the mass flow rate, net mass flow rate remained in the parallelepiped, okay? This is mass flow rate entering, this is mass flow rate leaving, mass flow rate entering and mass flow rate leaving. If you subtract this, and you will get the mass flow rate remained inside the parallelepiped, okay? So let's find out mass flow rate remained inside the parallelepiped. So let's subtract this and this, okay? So mass flow rate remained in the parallelepiped. Mass flow rate, net mass flow rate remained inside parallelepiped is equal to rho Bz dr into d theta into r d theta minus rho Bz dr into r d theta minus del rho Bz into Bz dr into r d theta by del z into dz, okay? So this is going to be cancelled out, and the only thing remained is minus del rho Bz dr into r d theta by del z into dz. This is the expression of net mass flow rate that has remained inside the parallelepiped, okay? So this is how you calculate the net mass flow rate remain in this parallelepiped. So we also have to calculate in other direction, that is towards this radial direction and towards this angular direction, okay? So that's why we have just done in this z direction. We have just find out the net mass flow rate remain inside parallelepiped in z direction, okay? We have to write this z direction also here. In z direction you have just found out the net mass flow rate remained in z direction. Now let's go to find out the net mass flow rate in this radial direction and this angular direction, okay? So we can find out the mass flow rate, net mass flow rate by considering likewise, okay? We have just found out the net mass flow rate remain inside the parallelepiped in z direction. So let's go to find out the net mass flow rate remained in this radial direction r and angular direction theta, okay? So for that you can write like directly, likewise net mass flow rate remained inside parallelepiped in r direction, okay? So in r direction you can write like directly here, like minus del rho br into, because in this radial direction, so that's why you have to write like rho br into what is the area in this radial direction, okay? The area is listen, this area is, this is dz, okay? This is dz, this is z into dz, and this is r d theta. So in this direction, in this radial direction, you must take the perpendicular area, that is r d theta into dz, okay? So r d theta into dz, you have to write like this, r theta into dz divided by del r, because you have been calculating the net mass rate toward the radial direction. So del r into dr, you must do this, okay? So this is in the radial direction. So in the radial direction you have to take the area, which area you have been taking, PSWT, okay? The area PSWT you must take, because this radius is perpendicular to this area. So you must take the area perpendicular to the flow. So that's why I have taken the area PSWT. This is the area PSWT. So I have taken the area PSWT, that is r d theta into dz in this case, okay? So likewise in the angular direction theta, net mass flow rate remained in the parallelepiped in which direction? Theta direction. In theta direction, that is, so you can write likewise here, that is minus del rho, you have been doing br here, in theta direction you have to write like b theta into what is the area in theta direction, okay? The area in this angular direction theta is must be the area PQUT. The area must be what? The area must be PQUT. Area PQUT. Okay, what is the area of PQUT? Look at this one. PQUT, that is dr into dz. Dr into dz is the area perpendicular to this theta. So dr into dz divided by del theta into d theta. Okay, this is the expression for the net mass flow rate in the angular direction theta. So Okay, you have calculated all the net mass flow rate. Let's add all these. Let's add all these. Okay, I have added all the mass flow rate entering from different phases of the parallelepiped. This is the net mass flow rate remained in the z direction. This is net mass flow rate remained in the r direction, and net mass flow rate remained in the theta direction. Okay, so from this equation expression we can separate dr dz into d theta. We can take the common here, and let's take the common minus also. Okay, after taking the common, let's write this expression by taking common minus and dr dz and d theta. Okay, so taking common out, that is minus del rho bz r divided by del z plus del rho br into r divided by del r plus del rho b theta divided by del theta, and taking common dr dz d theta. Okay, this is a common. We have taken dr dz d theta and minus common here, and let's again take the r common. Okay, let's take r common. Can we take r common from here? Yes, because this is in terms of z, expression differentiation in terms of z, so you can separate r from here. So del rho bz by del z plus del, but you cannot take this r outside because this is in terms of del r. So del rho br into r divided by r del r, because I have just put this r here because I have taken the r common. So del rho b theta by r del theta, and let's take the common, dr dz r d theta is the common, and let's make this equation number 1. Okay, this is the net mass flow rate remain inside the parallelepiped. So you can also find out the net mass flow rate directly by considering a small parallelepiped as a control volume. Okay, so let's find that one directly, and let's equate this with this equation. So for this I have to draw a small parallelepiped again. The small parallelepiped is like this, and that is dz and dr and r d theta. Okay, so this one is a parallelepiped we have been considering. So what is the mass of the parallelepiped? Mass of parallelepiped. Mass of the parallelepiped is volume into density. Okay, this is a control volume and it has got a density rho. So that is, volume is how much? dr dz and r d theta is the volume. Density rho into dr dz and r d theta is the volume. Okay, so this is the altogether, this is the mass of the parallelepiped. So we need to find out the mass flow rate. Mass flow rate, that is del m by del t. So that is del m is how much? M is rho dr dz r d theta by del t. So you can separate this density outside, that is del rho by del t, dr dz r d theta. This is going to be equation number 2. Okay, this is going to be equation number 2. So this is the mass flow rate of this control volume. Directly you can find out this mass flow rate like this. So let's equate equation number 1 and equation number 2 to get the expression. Equating equation 1 and equation 2, you get, let's write this equation at the top, del by del t, del rho by del t, that is dr dz r d theta is equal to minus del rho bz by del z plus del rho br into r divided by r del r plus del rho b theta by r del theta into, the common is dr dz r d theta is the common. So you can quote this dr dz r d theta. So you finally you find out that del rho by del t plus del rho bz by del z plus del rho br into r by r del r plus del rho b theta by r del theta is equal to 0. So this is for unsteady and compressible flow. Unsteady and compressible flow. of polar coordinate in continuity equation in polar coordinate system for unsteady and compressible flow. This expression is, and for steady and incompressible flow, you can just do this term 0, because this is not time dependency in the density is steady, the flow is steady, so there is no time dependency, and the density is incompressible density is constant everywhere, so you can take the density out from the expression. So that is del Vz by del Z plus del Vr into R divided by R del R plus del V theta by R del theta is equal to 0. This is our final expression of continuity equation. This is the final expression of continuity equation in polar coordinate system. Okay, so del Vr into R divided by R del R and plus del V theta R del theta and del Vz divided by del Z. This is the final expression of continuity equation in polar coordinate system. Okay, thank you so much for watching this video.